Welcome to Deep Dive Lab, where we break down and dissect cutting-edge scientific research. From advanced biomedical technologies to breakthroughs in AI, material science, chemistry, and physics, all told as compelling, easy-to-follow stories.
Exactly.
And I want you to start off today by picturing a massive Olympic-sized swimming pool.
Okay, I'm picturing it.
But instead of water, this pool is just filled to the absolute brim with billions of microscopic, brightly colored plastic balls.
Oh, boy.
Right. And your job is to sort every single one of those balls by color.
That sounds tedious.
Oh, it gets worse. You have to do it completely blindfolded. And, just to add a little extra pressure, you need to accomplish all of this while drastically cutting your monthly electricity bill.
I mean, that honestly sounds less like a fun game show and, well, more like some kind of cruel and unusual punishment.
It really does. But that impossible, highly frustrating scenario is actually a flawless metaphor for the daily reality of the global petroleum refining industry.
Yeah, that's a really good point.
Because they take raw crude oil, which is this chaotic, incredibly complex soup of different hydrocarbon molecules, and they have to separate it into distinct, usable parts.
And doing that takes a staggering amount of energy.
Exactly. To do that right now, they consume just a mind-boggling amount of power. So today on the Deep Dive, we are exploring a major question.
Right.
Why does separating crude oil require so much intense heat? And is it possible that a simple sponge-like plastic filter could step in and do that exact same heavy lifting at room temperature? Okay, let's unpack this.
Well, to understand the sheer gravity of this puzzle, for you, for me, and really for the entire global energy grid, we need to look at how we currently handle this sorting process.
The status quo, basically.
The industry standard right now is atmospheric and vacuum distillation. And it is just a pure brute force method.
Just boiling it, essentially.
Yeah, literally. You take the raw crude oil and you heat it to massive temperatures in a towering furnace. The goal is to boil off the different fractions, like naphtha, kerosene, and diesel, purely based on their boiling points.
I always think of it like trying to get the carrots out of a thick, complex beef stew.
Oh, I like that.
Right, because instead of just taking a slotted spoon and scooping the carrots out, the current method is basically putting the entire giant pot on a roaring bonfire.
And just boiling the whole thing down.
Exactly, boiling it until only the carrots remain. It just takes a staggering amount of energy.
Staggering is putting it mildly, honestly. Traditional distillation of crude oil consumes over 1,100 terawatt hours of energy every single year globally.
Wait, 1,100 terawatt hours.
Yeah.
Let's put that in perspective for you listening. That is actually more electricity than the entire country of Japan or, even a powerhouse like Germany uses in an entire year.
Just to boil oil.
Just to boil it. It's wild.
And the physical footprint of that energy use is enormous.
Yep.
I mean, the process emits over 160 million metric tons of CO2 equivalent annually.
That's massive.
It represents one of the most carbon-intensive, energy-heavy industrial processes on Earth.
Okay, so if the boiling method is that wasteful, why not just pour the stew through a strainer? Like, why haven't we just built a giant filter to separate the oil without all that heat?
Well, scientists have been chasing that exact idea for decades.
Have they?
Oh, yeah. The concept is called membrane-based prefractionation.
Okay.
Basically, you run the crude oil through a highly engineered filter before it ever sees a furnace. But there was this deeply entrenched dogma in the field of membrane science.
A dogma, like a rule everyone just accepted.
Exactly. The assumption was that to separate molecules that are chemically so similar to one another, you needed an incredibly dense membrane.
By dense, we're talking about a material where the pores are practically non-existent, right? Like almost a solid sheet of plastic.
Essentially, yes. They relied on glassy polymers and complex reverse osmosis style layers.
Right.
The prevailing logic dictated that to sort molecules purely by their size and shape at the nanometer scale, you just had to force them through a tight, highly restrictive barrier.
But I imagine forcing thick crude oil through a near-solid barrier creates like a massive bottleneck.
Oh, a bottleneck that completely killed the industrial viability of the idea.
Wow.
In membrane science, we measure the speed of filtration as permeance.
Permeance, okay.
Yeah, it calculates how many liters of oil flow through 1 square meter of the membrane per hour under 1 bar of pressure.
Got it.
And even with the thinnest possible dense selective layers, sometimes just 100 nanometers thick, the permeance for crude oil was hovering below 0.11.
Point one. It's like trying to drain that Olympic swimming pool we talked about earlier, but you're forcing all the water through a single coffee straw.
Yes.
You just can't move enough volume to run a global supply chain that way.
Exactly. The field was completely stuck. You either had a dense membrane that sorted the molecules perfectly but moved at a glacial pace, or...
Or you opened up the pores to speed things up.
Right. But then the membrane lost all ability to separate the complex oil mixture, just all rushed through.
So how did scientists figure this out? Because this is where the story gets really interesting. The solution didn't come from forcing a dense membrane to just, work harder.
No, it came from completely ignoring the conventional wisdom.
I love when that happens.
Me too.
Yeah.
In June 2026, a groundbreaking paper was published in the journal Nature. It was driven by a major international collaboration.
Who is involved?
We're talking about researchers like Dr. Ji-Hoon Choi, Dr. Hyuk Jun Seo, Dr. Dong-Yoon Ko, Dr. J.W. Lee, Dr. Ryan P. Lively.
Okay, wow.
And they were representing institutions like KAIST in South Korea, the Korea Research Institute of Chemical Technology, and the Georgia Institute of Technology in the U.S.
What really strikes me about their approach is how incredibly counterintuitive it is.
Totally backwards.
Yeah, instead of spending another, 5 years trying to engineer a better ultra-dense barrier layer, they basically threw out the barrier entirely. They tested a nominally macroporous membrane made of polyacrylonitrile, or PAN.
Which, to a chemical engineer, sounds absurd.
Yeah.
I mean, PAN has pores that are about 15 nanometers wide.
Which doesn't sound very big to us, honestly. But let me push back on that, because in the membrane world, PAN is usually just the cheap scaffolding, right?
Right, exactly.
It's the porous backing layer that scientists normally coat with those fancy, dense polymers.
The support structure.
Yeah. So using raw PAN to sort nanometer-sized oil molecules is like a construction crew stripping away the entire luxury high-rise building and trying to use the bare metal scaffolding to keep the rain out.
That's a great visual.
The holes are just too big.
Right. It is an ultrafiltration membrane, not a precise molecular sieve. If you push raw Arabian-like crude oil through a 15-nanometer tunnel, the physics dictate that the whole messy soup should just rush right through.
Without being sorted at all.
Exactly. But they ran the experiment anyway. And the mechanics of how they ran it are actually crucial here. Well, they didn't just dump the oil on top of the filter. They used a cross-flow filtration system.
Okay, cross-flow. The fluid dynamics here are what make the system viable, right?
Yes. In a standard dead-end filter, like a coffee filter in your kitchen, the liquid pushes straight down.
Right, gravity.
And all the gunk piles up on the surface, creating a thick cake that eventually blocks the flow entirely. But in a cross-flow system, the crude oil sweeps horizontally across the surface of the membrane.
Oh, I see. Think of a street sweeper driving parallel to a storm drain.
Yes.
The water and the small particles fall down into the drain, but the sweeper's forward momentum keeps all the heavy trash moving along the street so the grate never gets clogged.
That constant sweeping motion is vital. They set this system up, sweeping the raw crude oil across the bare PAN membrane at 40 bar of pressure.
Which is pretty high pressure.
It is, but they did it entirely at room temperature. No bonfires, no 1,100 terawatt hours of boiling heat.
And the numbers they saw were just staggering.
Unbelievable.
The permanence didn't just edge up a little bit, it skyrocketed to 0.591.
Yeah.
That is a 23-fold increase over the dense membrane benchmarks.
It's huge.
But the flow rate isn't even the main event here. It's what came out the other side of that scaffolding.
Exactly. They had thick, opaque, dark, raw crude oil flowing across the top. But the liquid that pushed through the membrane to permeate was a light-colored, visually distinct fluid in just 10 minutes.
In 10 minutes?
Yeah. The membrane had effectively sorted the oil, it held back the heavy sludge, and allowed highly enriched lighter fractions like naphtha and kerosene to pass through.
See, that defies common sense. You have a membrane with large 15-nanometer gaping holes flawlessly filtering out tiny molecules as if it were a high-end sub-2-nanometer dense membrane.
Right.
How does a massive tunnel suddenly act like a microscopic sorting gate?
Well, what's fascinating here is they uncovered something they termed a self-limiting pore constriction mechanism.
Self-limiting pore constriction.
Okay. Yeah. When the raw crude oil began flowing through those 15-nanometer pores, it brought along heavy, long-chain hydrocarbons.
sludge.
Specifically, molecules called N-alkanes, which have carbon chains between 17 and 33 atoms long.
Oh.
Instead of just washing through, these heavy waxes started to dynamically deposit onto the inner walls of the pores.
So the crude oil was literally leaving a highly specific layer of residue inside the tunnel.
Exactly. The oil built its own secondary tunnel inside the existing pore. The N-alkanes crystallized on the pan scaffolding, growing inward and shrinking that 15-nanometer opening down to a highly selective sub-2 nanometer gateway.
That is wild.
The human engineers just provided the rough template, and the complex chemistry of the oil organized itself into the perfect filter.
Wait, I have to challenge this.
Go for it.
We are talking about 40 bar of pressure. That is intense.
Very.
Like the pressure you'd feel hundreds of meters underwater.
Yeah.
If this new wall is just built out of crude oil wax residue, wouldn't that immense hydraulic pressure just instantly wash it away?
You would think so.
Right. How can they possibly prove this waxy layer is actually forming and staying there?
It is a valid skepticism.
Yep.
And it's exactly what the researchers had to prove. You can't just stick a tiny camera inside a microscopic pore to watch the walls close in.
Unfortunately not.
So they utilized some incredibly advanced analytical tools. The primary one was 3D time-of-flight secondary ion mass spectrometry.
Or TOFSIMS, right.
Or TOFSIMS, yeah.
Yeah.
Much easier to say.
Let's break down TOFSIMS for those of us who, don't keep one in the garage. How do you analyze the inside of a 15-nanometer hole?
Think of it like a highly precise molecular archaeological dig. First, they take the membrane after the oil has flowed through it.
Okay.
They shoot a beam of high-energy ions directly at the surface. When this beam strikes, it physically blasts off tiny fragments of molecules from the very top atomic layer.
Oh, wow. So it's literally knocking pieces of the material loose into the air.
Yes, and those blasted off fragments fly toward a detector.
Got it.
By measuring the exact fraction of a second it takes each fragment to hit the detector, their time of flight, the machine determines the exact chemical mass and identity of those molecules.
That is incredible. That gives you a chemical map of the surface.
Right.
But we still need to see inside the pore.
Right. So this is where the 3D aspect comes in. After they map that top layer, they bring in a second tool, an argon gas cluster beam.
An argon gas cluster beam.
Yeah. This beam acts like a microscopic deli slicer. It gently shaves away just a few nanometers of the surface material.
Oh, I see where this is going.
Then, the first ion beam fires again to read the newly exposed layer. They repeat this cycle, continuously shaving a microscopic layer, reading the chemistry, shaving another layer, reading it again.
They are digitally digging down into the membrane, layer by layer, building a 3D model of what is inside the tunnels.
Exactly. And the 3D maps they generated were undeniable.
What did they see?
Well, in a brand new, unused pan membrane, the dig just showed the chemical signature of the plastic. But in the used membrane, they found a massive, localized accumulation of hydrocarbon ions,
Glasses.
specifically C6H ions. This formed a distinct, heavy layer right at the opening and extending down into the pore structure. It visually proved the hydrocarbons were lining the walls.
But proving the molecules are inside the hole doesn't necessarily prove they form a solid wall, does it?
What do you mean?
Well, a thick, sloppy liquid sludge stuck in a pipe would also show up on that scan, right? How do we know it's a rigid filter?
Great question. They confirmed the physical state of the wax using X-ray diffraction.
Okay.
This technique shoots X-rays at the material and measures the angles at which the rays bounce off. The resulting scatter pattern tells you the atomic structure of a material.
So they can see the shape.
Right. When they analyzed this used membrane at room temperature, they observed distinct diffraction peaks corresponding to the rotator phase of N-paraffin.
The rotator phase. That sounds like a part of a car engine.
It does, but it's actually a fascinating state of matter. The heavy alkanes weren't a sloppy liquid sludge, but they weren't entirely frozen solid like a block of ice either.
Oh, weird.
In the rotator phase, the molecules are highly organized into a crystalline lattice, so the structured wall. But the individual molecules themselves are literally rotating in place around their long axis.
Wow. So they form a microscopic turnstile. It's a structured wall, but the molecules are spinning, which might explain how they interact with the lighter oil slipping past them.
Exactly.
But here is the major lingering question for me.
Shoot.
If these heavy waxes are crystallizing and building a wall inward, Why do they stop at sub 2 nanometers?
Oh.
Like, why doesn't the wax just keep accumulating until the entire 15 nanometer tunnel is completely checked off and nothing gets through at all?
This is where the thermodynamics come into play, and it's honestly the most elegant part of the entire discovery.
Okay.
The stopping point is dictated by the Gibbs-Thomson effect.
Okay, let's translate the Gibbs-Thomson effect for everyone.
Sure. Consider how water freezes in ice. Standard water freezes at 0 degrees Celsius. But if you trap that water in a truly microscopic space, say a nanometer wide crack in a piece of granite, the physical rules change.
The extreme confinement alters things.
Exactly. It alters the thermodynamic environment, significantly lowering the freezing point. The water inside that tiny crack might stay entirely liquid even when the surrounding temperature drops well below 0.
Just because the physical space is so small, it changes the fundamental behavior of the molecule.
Yes, and the exact same physical principle governs the heavy hydrocarbon waxes inside the pan membrane pores.
Oh, I see.
As the N-alkanes crystallize and build the wall thicker, the remaining tunnel gets tighter and tighter. As that opening approaches the sub 2 nanometer mark, the confinement effect becomes incredibly extreme.
The space gets so tight that the melting point of the waxes plummets.
Yes. The thermodynamic environment changes so drastically that any new wax attempting to attach to the wall instantly melts and is swept away by the cross-flow liquid. The shrinking of the pore creates a perfect thermodynamic equilibrium. It builds the tunnel down to precisely the right microscopic dimension, and then the laws of physics make it impossible for it to grow any further. It self-limits.
It's like an automated doorway that shrinks until it perfectly fits only the people you want to let through, and then just refuses to shrink another inch.
That's a great way to put it.
But does a self-built door like that actually hold up over time? Like, does it last?
The researchers actually ran the continuous crossflow for 4 straight weeks to test the durability.
Yeah.
The boiling point distribution of the filtered oil, meaning the precise chemical makeup of the lighter fluids passing through, remained virtually identical from the first day to the 28th day. The self-built wax filter remained entirely stable under 40 bar of pressure.
That is a phenomenal piece of chemical investigation.
It really is.
But I want to zoom out. Let's bring this out of the laboratory and into the real world for you listening right now. What does a self-assembling sub 2 nanometer crude oil filter actually mean for global infrastructure? Because we started this deep dive talking about 1,100 terawatt hours of energy and oceans of CO2 emissions, does this 15 nanometer sponge actually move the needle?
Well, it doesn't just move the needle, it fundamentally redraws the map. The researchers didn't stop at benchtop experiments. They took all their permeance and sorting data and ran extensive process simulations using Aspen Plus.
Aspen Plus.
Yeah, it's an industry-standard chemical engineering software used to model complex, full-scale industrial operations.
So they essentially built a virtual refinery to see what happens when you plug this plastic sponge into the real world.
Exactly. And the crucial element of their simulation is that they aren't proposing we bulldoze the world's existing refineries.
Which is good.
Right. They model the retrofit. This is vital because heavy industry rarely adopts new green technology if it requires tearing down their current infrastructure.
Right. If they can just bolt a new module onto the pipes they already have, the barrier to entry drops massively.
In the Aspen Plus model, they place this pan membrane unit directly in front of the traditional furnace. This is called pre-fractionation.
Before it gets heated.
Right. They simulated taking 16,000 cubic meters of crude oil a day and running it across the membrane at room temperature.
And what does the membrane pull out before the oil hits the fire?
The membrane acts as an enormous shortcut. It strips out the valuable, lighter fuels than naphtha, kerosene, and diesel fractions. In this simulation, they achieved a 61.5% stage cut.
Let's clarify stage cut for a second. That just means that over 60% of the total liquid volume is successfully separated out during this first room temperature stage.
Correct. Over 60% of the usable fluids bypass the furnace entirely. That leaves only the heaviest, thickest sludge to continue down the pipe to be heated.
Wow. So the furnace doesn't have to boil the entire massive volume of raw crude oil. It only has to heat the remaining 40%. The reduction in fuel needed to run that furnace must be huge.
In industrial terms, we call that the reduction in heat duty, the raw amount of fuel you have to burn to get the furnace up to operating temperature.
Okay.
By bypassing 60% of the oil, the Aspen Plus simulation showed a 31.6% reduction in overall energy consumption compared to traditional atmospheric distillation.
31.6%. When an industry uses 1,100 terawatt hours, Slicing off a third of that energy requirement is a colossal amount of global power saved.
And the thermodynamic ripple effects don't stop at the furnace.
Oh.
Because you aren't boiling all that extra liquid, you don't have to use massive industrial cooling towers to condense it back down on the other side.
Oh, right, because it never got boiled.
Exactly. That resulted in a 20.7% decrease in the cooling water needed. We are talking about tens of thousands of cubic meters of fresh water conserved daily.
That's incredible. And if you are burning a third less energy, the carbon emissions have to mirror that drop.
The calculations point directly to a 37.6% drop in overall CO2 emissions for the process.
Let's just frame the sheer scale of that for a second. By placing a specially engineered plastic scaffolding in front of the heater and letting the oil build its own filter, an entire global industry could potentially wipe out over a third of its carbon emissions.
Based purely on the thermodynamic data, yes. And perhaps the most compelling factor for actual real-world adoption is the financial model.
Right, because money talks.
Always. The reduction in heat duty and energy consumption translates directly to a 36% lower annualized operational cost.
Wait, really? A major climate solution that simultaneously slashes operational costs by over a third?
Yeah.
You rarely see an environmental upgrade align so perfectly with the economic bottom line. Usually, drastically reducing carbon intensity requires immense capital expenditure and drives up running costs.
It is an incredible rarity. This approach leverages the free energy of thermodynamics to do the difficult sorting work, rather than relying on brute force fossil fuels.
We have covered a massive amount of ground today, from blindfolded ball sorting and a swimming pool to the intricacies of the Gibbs-Thomson effect. Let's summarize the 3 key takeaways we want you to walk away with. First, sometimes the overlooked, unsung material is actually the missing puzzle piece. For decades, scientists dismissed the cheap, highly porous pan backing layer, assuming its 15-nanometer holes were too vast to filter anything complex, but it turned out to be the perfect scaffolding.
Second, self-building nanopores demonstrate that chemistry and thermodynamics can create perfect structures if we establish the right conditions. Instead of forcing a dense, painfully slow membrane to do the sorting, the crossflow system allowed the heavy hydrocarbons to dynamically construct their own sub-2-nanometer gateway, one that perfectly regulates its own size.
Right. And third, intelligent retrofits have the power to instantly and drastically alter the massive carbon footprint of legacy industries.
Absolutely.
By pre-fractionating the crude oil at room temperature, we can bypass a massive amount of the heating and cooling that drives industrial emissions, potentially saving vast amounts of power and millions of tons of CO2.
If we connect this to the bigger picture, it forces a profound reflection on human engineering. Our default instinct is almost always to exert control. We try to force solutions by designing incredibly complex, dense, impenetrable barriers. We try to over-engineer nature.
We really do.
But the breakthrough here was elegant. By simply providing the right scaffolding and applying a steady cross-flow pressure, the chaotic mixture actually organized itself into the perfect filter.
It's a striking reminder that sometimes the smartest engineering is just setting the stage and getting out of the way so physics can do the heavy lifting. Which leaves me with a final provocative thought for you to ponder.
All right.
If crude oil, one of the messiest, most chaotic liquid mixtures on the planet, can be coaxed into building its own flawless filtration tunnel inside a simple polymer sponge, what other dirty, incredibly complex chemical mixtures out there could be tricked into cleaning themselves?
That is a great question.
Right. If we stop trying to force the filter, what else might self-assemble?
It really challenges us to look at industrial separation in a completely new light.
It really does. And with that, we want to thank you for joining us in the Deep Dive Lab today. We hope you enjoyed unraveling this molecular mystery as much as we did. Please make sure to follow and subscribe for more science stories as we continue to explore the breakthroughs that are quietly reshaping our world. Until next time, stay curious.